Hey everyone, welcome to the vodcast on acid-base theory. Towards the end of this vodcast, you're also going to get a second introduction and review on various types of concentration and units that we use and formulas. All right, get your notes ready. Let's begin. So this is just a little recap. When we measure pH, we have done so in previous activities up to this point. We've been using pH paper. We've also been using red litmus paper, blue litmus paper. So you're kind of used to all of those. And I just wanted to make sure that you knew that there are also some other equipment available called pH meters. They can also do the trick. They're electronic and they have to be calibrated, so we didn't really use them in our labs because they're kind of tricky to use. But they also are a second option. So I know you guys have seen many different indicators. You guys have seen phenolphthalein, but there are many other types of indicators that we can use. And when we are using those indicators with our acids and bases, you need to understand one thing. Acids, when they dissociate in water, they will either create a hydrogen ion or a hydroxide ion. So in the little formula that I have down here, I'm showing you how water dissociates. And we've talked about this before. Anytime you see that double arrow that you see right there after the water, this means that you have something called an equilibrium, where the forward reaction is occurring at the same time as the backwards reaction. So what we like to say is that the rate of the reaction making products is the same as the rate of the products making reactants. It goes back and forth. So when we use indicators, we're looking for an acid that's able to produce a lot of hydrogen ions for an acid, or for a base, something that's making a lot of hydroxide ions. But sometimes acids and bases have a hard time making those ions, and that's what makes them weak. So in our previous activities, you did discover that vinegar was a fairly weak acid. Vinegar is made with acetic acid, and acetic acid is infamous for being a fairly weak acid. We also took a look at various bases, and one of them that we were looking at was the ammonium hydroxide compound. And that was not a very strong acid, strong base. And so those particular types of bases, they don't produce very many ions in solution. And so we can actually determine whether or not they're strong or weak by looking at their conductivity levels. So I did post my poster in the classroom. If you never got a chance to look at it, go ahead and check it again. But there are many different indicators that you can use when we are working with acids or bases. And the ones that you guys were using were, there was a couple different. We had red litmus paper and blue litmus paper. And you'll notice that in this picture, litmus is located right in the middle, kind of next to methyl red and bromothymol blue. And I hope you understand now, when I think I mentioned this in some of my classes, when I think about acids, I think about the color red. And when I think about bases, I think about the color blue. And it's kind of hard to remember that, but I like to think, base is blue, BB. So that kind of helps me remember it's either red or blue. But anyway, sometimes we can combine some of these indicators to create a very broad spectrum of various different colors. And that's actually how they make regular pH paper. They combine various different types of indicators so that we can get a range of color to help us determine what the exact pH is of that substance. So now moving on a little bit, we're going to start talking a little bit about acid-base theory. So one of the first people that we're going to talk about is Svante Arrhenius. He won the Nobel Prize in Chemistry in 1903 for a lot of his discoveries about electrolytes. Imagine that! We've actually talked a lot about electrolytes. Electrolytes are ions that dissolved in water, and they produce conductivity. So he discovered that certain substances dissolve in water to yield a solution that conducts electricity, which we call, electrolytes. But he also discovered that many of the acids are really strong acids, and some of the acids were not very good at conducting electricity. And so he finally decided to come up with his own theory of what an acid or a base should be. And so he came up with the very first definition that was scientifically published. So for Svante Arrhenius, he said that acids are hydrogen-containing compounds that ionize to produce hydrogen ions in solution. So anything that makes hydrogen ions, he defined as an acid. He also said that bases are compounds that ionize and they produce OH ions in solution. So there's his basic definition. So here's something that poor Arrhenius didn't even know yet. Not all compounds contain hydrogen, are acids. So I have an example coming up, but before we get to that, let's talk about some common acids that you guys are pretty familiar with. So, for example, we have hydrochloric acid. When you stick hydrochloric acid in water, it's going to produce hydrogen and hydrogen ions and chlorine. So it's easy to see this in this particular reaction, how I drew it. But I don't think you guys have ever seen H3O+. That's something that's kind of new. H3O+ is the same thing as an H+ ion. Some textbooks don't like to write just an H+. They think that, H+ should always be associated with something because an H+ ion, as we know as hydrogen ion, is actually very highly reactive. So reactive that it actually doesn't like to stand alone. Just like when we were first learning about diatomic molecules, when you have a hydrogen ion, it is going to eventually find its way to some other substance to cling on to. And that substance, when it's in water, is water. So water plus an extra hydrogen will give you H3O. And since that extra hydrogen has a positive charge, well, H3O gets its positive charge. But anyway, only hydrogens in very polar bonds are going to ionize. And so we do categorize certain acids as either being strong or weak, and the strong ones are the ones that come from polar bonds. If you have highly polar bonds, you're probably going to have a fairly strong acid. So if the acid is not capable of creating ions very well in solution, it's going to be categorized as a weak acid. So remember how I said sometimes acids not all acids have to have that hydrogen in there? Well, this came to light with Bronsted-Lowry. These two gentlemen came around 1923. They wrote a couple papers about acids, and they were investigating and furthering some of the research that Arrhenius brought along. And one of the major substances that they realized that there was a problem with was ammonia. And here's the problem that they saw. In my example down here, this is the formula for ammonia, NH3. And when you first look at that formula, you're like, I don't know. It doesn't have a hydroxide on there, and it doesn't have the hydrogen written in the front. So what's up with this thing? Is it an acid or is it not? But ammonia, when it's tested with certain, indicators or pH paper, you'll always get blue. And remember what blue means. Blue means base. And so these guys had to come up with a new definition for an acid and base. They redefined it. They said an acid is a hydrogen ion donor and a base is a hydrogen ion acceptor. So what I'm going to do is I'm going to try to explain that using the example that you see down here. Let's get that written down in our notes. What you're looking at is the dissociation of ammonia in water. So right here, your water is actually capable in the formula of actually disassociating and throwing off one of these hydrogens. One of these hydrogens is going to attach itself to the NH3, making your favorite ion, the ammonium ion, one of the only polyatomic ions that we have. And then, sure enough, guess what's left over? Your hydroxide. So the hydroxide comes over here, and this is how ammonia actually creates hydroxide. It's kind of tricky. Basically, the ammonia is literally ripping apart the water, and in that process is creating your hydroxide ions, making that ammonia appear like a base. So that phenomenon, that process, doesn't really fit into the Arrhenius definition of an acid or a base. I mean, it's producing the hydroxide, but the hydroxide wasn't really easy to find inside of the formula for ammonia. So a new definition actually had to be created, and believe it or not, poor Arrhenius actually thought that ammonia's real formula was NH4OH. Can't say that I blame him very much, but the molar mass of ammonia was discovered to be way less than NH4OH. It was just NH3. So, according to Bronsted-Lowry, does this actually mean in that reaction that we were just looking at, is the is the water actually behaving like an acid? Because according to Bronsted-Lowry, acids are hydrogen ion donors. Well, yeah, water's acting like an acid. And what's fascinating here is that there is a double arrow. Let's take a closer look at that double arrow because that's actually a very important area. Not only does the forward reaction occur, but the backwards reaction also is occurring at the same time. So just remember that an acid is a hydrogen donor. So if you think about this reaction occurring in the backwards direction, in this way, let's look at ammonium. The ammonium ion has 4 hydrogens, but over on the left side, you see how he now only has 3. The reason why is because the ammonium ion actually took one of its hydrogens and gave it to the OH. So this guy's behaving like an acid. And since the OH accepted that hydrogen ion, this guy would be behaving like a base. So in the reverse direction, ammonium would be the acid and hydroxide would be the base. But as you know, in the forward reaction, this guy is your base and water actually behave like an acid. You see, the thing about Bronsted-Lowry is that acids and bases, they always have a pair or kind of like a doppelganger twin on the other side of the reaction. We call these acid-base pairs. Well, the technical word we use is conjugate acid-base pairs. So if the reaction is going in the reverse direction, the NH4 is going to give up a hydrogen ion, so that makes it kind of like an acid. And the hydroxide ion is going to accept the hydrogen from the ammonium ion, making it kind of like a base. So just a little further explanation here. Starting on the left side, we know that the water was originally behaving like an acid, and we know that the ammonia was originally behaving like a base. So these are your original acids, and this guy is your original base. Now, on the right side of the formula, whatever the original acid or base turned into would be its conjugate pair. So the water, its conjugate base, because it is behaving like a base in the backwards direction, is the OH. So this guy right here is your conjugate base. And then this guy right here, because he was made from the base, he is called your conjugate acid. So here's the thing that always happens. The acid will make a conjugate base, and the base will make a conjugate acid. They flip, they reverse roles, and that's always true. All right? Now, unfortunately, there is one more definition to acids and bases, and this is the hardest one to explain, and it comes from the gentleman by the name of Gilbert Lewis. And he decided that the current definitions of acids and bases were not completely lined up for examples that I'll show you. He defined a Lewis acid as a substance that can accept a pair of electrons from a covalent bond and a base that can donate a pair of electrons to form a covalent bond. So an acid, it accepts it, and the base donates. All right, this particular type of acid and base is not highly taught at the high school level. This is more of a pre-college kind of organic chemistry, physical chemistry type subject, but I think it is kind of interesting. So here we are again with our ammonia. That's what you see right here. That's your base. And right next to him is this weird acid. Technically, this guy, when you test him in a solution with water, he will actually kind of rip the hydroxide and then take the hydroxide and then leave behind the hydrogen ion. So he's a hydrogen ion producer. But anyway, when you bring these two together, they'll make this really interesting compound right here. So in this particular reaction, the ammonia is behaving like the Lewis base. So I know it gets kind of confusing, but let's look backwards here just a second. the base is going to take this pair right here and form a covalent bond with that B, that's what, boron. And so since the base is donating the pair of electrons to form a covalent bond, and then the acid here is accepting those hydrogens, or I mean those electrons, you've created a Lewis base and a Lewis acid. So this is not a very common type of acid, and it's usually only found in really complicated compounds and really complicated chemical reactions. So I'm not really going to emphasize it very much. Here's a good little wrap-up, if you will, a recap of everything that I've taught you about acid-base theory. So for Arrhenius is the most basic definition of an acid or a base. Those guys, the acids make hydrogen ions and bases make hydroxide. But then for Bronsted-Lowry, the definition changed just a little bit. Acids are proton donors, which is just a hydrogen ion. That's really what a hydrogen ion is. Think about it. Hydrogen has one proton, one electron. If you rip an electron away, which is what a hydrogen ion does, you know, it loses one electron. If you rip that electron away, it's just a proton sitting in space, which is kind of interesting. But anyway, so acids are proton donors and bases are proton acceptors, or if you don't like the word proton, you can just call them hydrogen ions. But anyway, and then finally we also have the Lewis definition of an acid and a base, and acids, they accept a pair of electrons and bases donate a pair of electrons. Enough said, huh? So now what we're going to move on to is a small recap on concentration. You guys already know about molarity and molality. Make sure you have these definitions and formulas memorized for your upcoming exam. But now we're moving on to a few new things. So concentration is sometimes expressed in different ways, and one of those different ways that we're going to discuss here is percent by volume. All right, so percent by volume is when you take the volume of the solute and you divide it by the volume of the solution, and then times it by 100. Please make special note here that we are talking about the volume of the solution on the denominator, so make sure you're getting that right. The solution is both the solute and the solvent combined. So an example is wine has a 12% volume of ethanol. That means that for every 100 milliliters of wine, you'll have 12 milliliters of ethanol. Another example would be the rubbing alcohol that you get sold at the grocery store. So rubbing alcohol is typically sold at 70% volume. So there's a couple different ways you can think about it. If you had 700 milliliters of isopropyl alcohol, you would put enough water into the 700 milliliters to make the final volume 1,000 milliliters, and that by definition would be 70%. Now, easy math would be to just take 70 milliliters of isopropyl alcohol and add enough water to make the total volume come up to 100, because that is also 70%.